Hello, and welcome everyone to section 1.2 functions. Today, as our introduction to functions, we're going to take a quick look at a relation. We're going to define a relation to be a set of ordered pairs, so x comma y, in which then the domain of the relation is the set of all x coordinates. The range of a relation is the set of all y coordinates. And then we'll talk about how a function is a relation in that each domain element corresponds to one and only one range element. Several things from Algebra 2 and also Algebra 1 will be touched upon in this particular section. And we jump right in here. Example 1, capital S, which basically just tells you the set of ordered pairs, and then you see the notation that you're more familiar with inside, so that 1 comma 3, negative 5 comma 4, 7 comma 3, those three xy coordinates are the ordered pairs, of course, in this particular set. So what is the domain of S? Pretty simply, the domain is going to be the x coordinates. So we're going to go ahead and use set notation. And we'll start with the x that's the smallest, so negative 5. And then work our way up to 1. And then lastly, 7. Okay, now this notation is something we need to be familiar with. We are going to be using other notation throughout this course, but today that's what we'll start with. For part B, it asks what is the range of S. So now we're talking about, of course, the y coordinates. Starting again with the smallest, 3. And then because there's two y coordinates of 3, we'll just write 3 once. And then we'll go ahead and finish this set off with, of course, the other y coordinate 4. Part C. Is S a function? Okay, so if we recall back to the definition up above, a function is a relation in which each domain element corresponds to one and only one range element. So if we look at the respective ordered pairs, again, 1, 3, negative 5, 4, 7, 3, we can see that the x coordinates are all different, which really is as easy then as us jumping to the conclusion and saying, yes, this is a function. No matter what the y coordinates are, the x coordinates, of course, well, those are the same in some examples that follow, but because they're different, it doesn't matter what the y coordinates are. So yes, this is a function. Okay. If I did have any repeat x coordinates with different outputs, then it would not. We didn't see that here, but we'll talk about that down the road. Next page. So I'm stating that because the solution sets of equations in two variables are sets of ordered pairs, such equations define relations. In addition, some will define functions. In this case, the variable representing the domain element x is called the independent variable. And you may recall that, again, from your previous courses. So independent would be the x. The variable representing the range of elements, or y, is called the dependent variable. And we'll talk about how that relates, of course, on the graph of various relations and functions. An equation in two variables, x and y, represents y as a function of x if it can be uniquely solved for x. So example 2. Which of the following equations represents y as a function of x? So when we look at this, we can at least attempt to get y by itself here in the following way. So y equals, and I'll subtract 2x squared, but also subtract 1 at the same time, which will yield y equals negative 2x squared minus 1. The equation is uniquely solved for y, as we say. So we say that y is a function of x. Y is a function of x. You're probably more familiar with the test that we use for these types of equations called the vertical line test. We're not going to do that yet, but that is something you could definitely do on something like this, in which you would see then that it goes to say that it sticks to the definition from above that each input does in fact have one output, or again, each domain element corresponds to one and only one range element. I'll say input and output a lot actually as we go through when I'm discussing x's and y's. Part B. So x plus y squared minus 6 equals 0. So I'm going to go ahead and attempt again to get y by itself. Subtract x, add 6. I'll do that same time so that y squared equals negative x plus 6. Now I still have yet another step to perform here, which should be the square root of both sides, yielding y equals. And remember, here's the nuance to this. You gotta place a plus or minus in front. So plus or minus the square root of negative x plus 6. Now, if you think about our definition from up top again, speaking to the fact that each domain element corresponds to one and only one range element, or each input must have only one output, we must take a look at the fact that because I have two different signs on my square root expression, if you plug in a number for x, not only are you going to get a plus, plug in an x, the same x that is, and you're going to get a minus or a negative. So there's actually two outputs per input. And I'll go ahead and circle the plus or minus and note that. So we'll say no. Y is not a function. And again, two outputs. I think that'll be easy enough for us to relate back to if necessary. Next, function notation. Discuss, as we're about to do here, naming a function so that it can be referenced. Name the function f. Since we say that y is a function of x, we can replace y with f of x, is how we say that when it's in parentheses. Now, if we need to know the value of y in the f function when x equals a, all we have to do is write f of a. This value is read f, as I just said, of a. Now, we're not just going to be using f in terms of identifying functions. Plainly, it's just a letter we use to differentiate. We use it a lot, but sometimes we'll use g, sometimes we'll use h. So let's go ahead and take a look. I do have a tip to reference. And this tip here says that there are two things that you cannot emphasize too much. One is y equals f of x. The other is that f is the name of the function, not another variable. So that's important. So we're actually using f of x to replace y. So when we see in the next example here, if f of x equals x squared minus 4x, find the following, we can actually interpret it as such. And we should. Y equals x squared minus 4x. So when we do our analysis on, for example, here, f of 3, yes, we're going to be plugging in 3 for x, so it becomes 3 squared minus 4 times 3. We'll do our math, which is really as easy as squaring the 3, and then of course 4 times 3, 9 minus 12 from there, negative 3. So we could also write y, or I'll simply say f of 3 equals negative 3. But in essence, what we did just find, in fact, is the y coordinate. The interpretation then could be, if you were to follow up, would be, well, the x coordinate was 3 and the y coordinate was negative 3. So it is an ordered pair on the function y equals x squared minus 4x. Notationally, we do like using f of x or g of x and so on, just for the sake of being able to say, okay, this particular input for that output, so I don't necessarily have to write the ordered pair all the time. And it's even more conducive to problems of this nature, as you see in Part B, where you're not even plugging in a number, you're plugging in a variable. So here's how that's going to work. So f of a, we'll say in the quantity again, now though a, quantity squared, minus 4 times a. It is going to just then, if you simplify a bit, a squared minus 4a, it is just then going to look like this, and that's our final answer. That particular expression obviously looks a whole lot like the initial expression, y equals x squared minus 4x, but certainly something we'll need to pay close attention to and utilize down the road. Speaking of which, in the next example, we'll continue on. This time a little bit more complicated looking. We've got x plus h, a binomial. Binomial has two terms, pretty much, as you notice. If you don't recall, that's what it is. And then we go ahead and do the same basic thing. Now, granted, we're plugging in this quantity, and I'm going to put it in parentheses. Okay, now, I know that the original problem actually did have an x, but that's totally fine. We do, in fact, have an x here, but the simplification will work out as if, let's say, you were not starting with x at the very beginning. So with x plus h quantity squared, I'm definitely going to have to FOIL this. Please be mindful of that. And I'll go ahead and distribute the negative 4 as well in this step. Continuing on, I've got x plus h times x plus h. So first, x squared, outside, xh, inside, xh, and then last, h squared. I'll rewrite my last two terms. Continuing to simplify here, I have just 1x squared. I've got like terms here with xh, xh, which adds 2xh. I have the h squared, the negative 4x, and the negative 4h. So if I just take a look again, though, at all of these respective terms, it doesn't appear that I have any more like terms, right? X squared, 2xh, h squared, x, and h. If we happen to have the exact same base with the same exponent, then we could in fact add those. If I had another h squared, for example, I would of course add it or subtract it, depending upon what the signs are. So that's our final answer, and that's totally fine. Next example. So we're looking at what we call here a piecewise function. You may recall this from Algebra 2. If f of x equals the following pieces, x plus 1, with then if x greater than or equal to 0 as a restriction or constraint, you can call it. The second piece being negative x, or y equals, you could even say. This again being a substitute for y. So y equals negative x. If x is less than 0, we want to find the following. So the first is find f of 2. Now, if we wanted to plug in 2 into either one of these pieces, we say, we have to be mindful of the fact that we do have a restriction, right? So the first piece, x was greater than or equal to 0, and the second, x is less than. So because 2 is in fact greater than or equal to 0, I just said x equals 2, which is greater than or equal, of course. So we're looking at only then piece 1 being our expression to substitute in for. So that's going to look something like this. I'll put it in parentheses. In the future, you're going to definitely want to use parentheses for more complicated expressions. The last example actually spoke to that pretty clearly. But go ahead and go finish this off with, of course, our answer. Last problem on this page, f of negative 5. We know that negative 5 is less than 0. So that means then I will be plugging it into the second piece. Of course, as I said, less than 0. Because the second piece is just simply negative x, we say negative of negative 5, which ends up being 5.